This is Lecture 9, Part 1, and in this particular slideshow I'm going to introduce some of the concepts of magnetism that are applicable to the discussion of spin resonance, both electron spin resonance and nuclear spin resonance. So starting off with the original arguments regarding how magnetism works, it was known that if you took a soft iron bar, which is not magnetic, and place it in an electric coil that generates an electromagnetic field. The coil carries a current, generates a magnetic field, and that magnetic field of the current gets augmented by the iron as it becomes magnetized. So something is taking place within the soft iron that augments the existing field, reinforcing it, in other words. If one removes the coil, namely the external source of the magnetic field, the soft iron will retain the magnetism, this is referred to as remnant magnetism. But if you damage the magnetized iron, either by heating it or by dropping it and having a shock wave, for example, you can lose the magnetism that has been created. So something about the dynamics of the particles within the soft iron are responsible for the magnetism. In the late 1800s, the idea of the molecule was starting to come to fruition, so to speak, and Weber, an electromagnetic theory person, postulated that there were things like molecular magnets within the macroscopic magnet like iron. And he argued no particular source. He drew them as little pogs, like little tiny compass needles, and various origins were suggested, namely there could have been current loops within the grain structure of this iron. There was really no argument, no solid evidence, in other words. But the mechanism, the phenomenon that was outlined in the previous slide was argued on the basis of these molecular magnets, namely that if you put the soft iron into a magnetic field, the molecular magnets orient, thereby giving you a macroscopic magnetized sample. And there are two types of phenomena or types of magnets. The first of these is paramagnetic or paramagnetism, in which the induced magnetism disappears once you remove the field. So in other words, it's never stable. Once you remove the external field, the molecules randomize and go back to where they were, giving you a non-magnetic material. On the other hand, there's ferromagnetism, in which the magnetism remains in the object after the external field is removed. And this is because the molecular magnets self-induce and they hold themselves in the position that they have been given by the external field. In around 1900, as the atomic structure is starting to become realized, namely the presence of a proton and an electron, electron circling the other, the origin of the magnetism is associated with the orbital motion. So the electrically charged electron, negatively charged electron, circling the nucleus creates a current loop of its own, so that as it circles the nucleus, it generates a magnetic field, as indicated by the arrow. So this would be orbital magnetic moment. The problem with this orbital magnetic moment is that mathematically it did not correspond to what was observed spectroscopically, so there was something else present and missing from the original atomic structure. And the missing component was deemed spin magnetic moment. And so using the planetary model applied to the theory of the atoms, the Earth revolves around the sun, so it has orbital motion. It also has rotational motion, and we know that the Earth also has a magnetic moment of its own, the magnetic poles. So it was argued that the electron must have volume, and it must be, or can be thought to have, spin motion as it rotates, as it moves in its orbit. So like the planet Earth, it has orbital motion and spin or gyroscopic motion. So there is a spin magnetic moment indicated by the vector through the little ball representing the electron, and the orbital magnetic moment. And so this becomes associated with magnetism in the valence electron shell, since according to the Pauli principle, the electrons pair in each orbit and the magnetic moments would cancel as they are paired. So you have to have an unpaired electron to have a electron magnetic moment. And so the revised model is a combination of orbital and spin magnetic moment. The total magnetic moment would therefore be the vector sum of these two moments, and the degree of which they are attached is what's known as spin-orbit coupling in the quantum mechanics. So the spin and the orbital motion combine to give you your magnetic moment at the atomic scale. Once they're polarized, the microscopic magnets, or the molecular magnets, however you want to call them, have little tiny dynamic motions, what we would call oscillatory motions. And these can be first compared to and seen in macroscopic magnets, namely, say, a compass needle or a bar magnet pivoted on its center of gravity. So in the classic magnetic dipole, there's a north-south separated by some distance. The object has a weight distributed over a volume, or in this case, two-dimensional model, an area. And when it is put in the magnetic field, it develops a little bit of a wobble. So it behaves like a pendulum. And the pendulum motion has a characteristic frequency like any pendulum or an oscillator. And the frequency is related to the strength of the magnetic field and the moment of inertia in this particular case, or the magnetic moment if you want to multiply the magnetic dipole strength by the moment of inertia for the relationship. So again, it's like a classical oscillator. There are two dependent terms, namely the size of the magnetic moment and the magnitude of the external field orienting it. So that when you have classical magnets, the external field orients them and then sets them into a characteristic wobble frequency, precession, or pendulum-like or oscillatory motion. And so if we apply this to Weber's molecular magnets, it's the same idea. You orient the field, they go into motion, and if you take away the field and the magnetism remains, or the magnetization remains, you have what's known as a ferromagnet. If the removal of the external field results in the loss of magnetism, you have a paramagnetic material. And so now if we look at it from the standpoint of the quantum mechanics, namely apply the concept of spin and observe what happens with these spin magnetic moments, we apply the field, the spins orient themselves or polarized in the magnetic field, but there's a subtle difference here. And that subtle difference is the fact that some of them are pointing in the opposite direction, and their alignment in the second case is that the alignment is at an angle. So this is actually referred to as spin quantization. The alignments of spin take on specific values. In other words, they can't be continuous. You can't get all possible angles. You can only get certain angles relative to the applied magnetic field, which is taken as the z direction, just as a side remark. And some of them are pointing backwards. And the reason some of them are pointing against the magnetic field is that the energy difference between these two states, as we would call them, is so small that you don't fully populate the ground state. You'll get some in the excited state, namely the directions pointing backwards. You do get the precession, so the phenomenological aspect of it is all the same, but the difference between this and the classical world is that you have specific directions. and it's roughly 68 degrees, I think. So these directions give you a different type of wobble motion as a result, which we'll see in the next slide. So again, in the quantum world, we have the polarization of the spin. The z-axis is designated as the direction of the applied magnetic field, which I'm not going to draw here. And the spin itself, or the electron, is actually tilted, as indicated. And as a result, there's a projection of the magnetic moment onto the x and y plane. There'll also be a projection onto the z-axis. So you can resolve the magnetic moment of the electron onto its different components into the coordinate system. But more importantly, the fact that it's tilted like this means that the wobble, as represented, actually traces out a circular path, a lot like a top. So if you have a top spinning on a tabletop, and if it gets knocked to the side, it's not only spinning, but it tends to wobble around the vertical axis. If we now take away the solid rigid body and look at a more simple diagrammatic representation for the spin, we can represent the magnetic moment as the arrow, a vector. So in this case, it'll be this white vector in the cartoon. And we can resolve a z component along the z-axis, which just remains stationary as the white vector precesses around the z-axis. And then we have the projection onto the xy plane, and this is going to rotate like a clock around the plane as the white vector precesses along that yellow path. The phenomenon is referred to as Larmor precession, and like the classical wobble, the frequency of the precession is proportional to the applied magnetic field strength. And so in this diagram, I'm looking down the z-axis, and what I'm referring to as the projections onto the xy plane are seen as the blue arrow. The projection onto the z-axis, which remains stationary, is going to look like a hub pointing out at you. And so during the precession process, the xy component of the magnetization is going to rotate in this particular case, a counterclockwise fashion. So in summary, the charged nucleons, namely the protons and electrons of the atoms, possess a magnetic moment attributed to spin. They also have orbital angular momentum, but in most cases, the orbital angular momentum is small and doesn't get included. You only see orbital angular momentum included in the magnetic moments of electrons associated with transition metal ions. In the case of atomic nuclei, the quantum mechanics applied to atomic nuclei does give you orbitals. So if you go into nuclear physics, you will find that you can write orbitals for atomic nuclei, but those orbitals are tiny, and the energies are so great that they're just completely taken out of the picture when you talk about the magnetism. So we talk about spin magnetic moment only in the case of atomic nuclei. So proton magnetic resonance is called nuclear magnetic resonance, nuclear spin resonance. If you impose an external magnetic field on these microscopic magnets, namely the atoms, you polarize the direction and the nuclear magnetic moments. Because of the charge differences, they point in different directions, just recall. The allowed directions are defined according to spatial quantization, so you can only get certain positions which correspond to the different spin states in quantum mechanics, and you can only have transitions between these usually two states in case of spin 1/2, but if you have spin 1, you'll have additional states. So the transitions are limited. You cannot turn the magnetic moments in any arbitrary angle. And then the polarized spins acquire an oscillatory motion. We call it precession in case of magnetic resonance. And the frequency of that oscillatory motion is proportional to the strength of the magnetic field. And so this concludes our very brief summary of magnetism and its origins as phenomenological behavior. In the next part, we'll discuss spin resonance. We'll go back to the vector diagrams only and describe how the spins behave when they are grouped. So I showed you the vectors in this slideshow of a single magnetic moment. And we're going to discuss what happens when you have a collection of magnetic moments and how the application of a radio frequency field will alter the population of the magnetic moments. And of course, here's the usual bibliography on some of the topics and concepts I discussed in this slideshow.